Welcome back to linear algebra. Let's jump into Anki to begin with. Here are the columns of how are the columns of matrix A affected if it is multiplied on the right by diagonal matrix D? Each successive column will be multiplied through by each successive diagonal entry. What are the commutative law for are the commutative law for addition, the associative law for addition, the associative law for multiplication, and the left and right distributive laws for matrices? Alright, commutative law for addition. A plus B equals B plus A. Associative law for addition. The sum of A plus B plus C equals the sum of A plus the sum of B plus C. The associative law for multiplication. The product of A times B times C equals A times the product of B times C. And left and right distributive laws for matrices. Distributive law. A times the sum of B plus C equals A times B plus A times C, and the sum of A plus B times C equals AC plus BC. Nice. Must the inverse of an invertible symmetric matrix be symmetric? Yep. Alright, that's that for Anki. Then I'm going to grade the work I did from yesterday, and then we'll go from there. Alright. I got everything right from yesterday, so I'm going to keep working on this proof that I started yesterday. Talk to you in a bit. Alright. I finished the proof. It might be not valid, but I understand a decent more about the proof itself, and I'll have ChatGPT check it tomorrow. But I just wanted to get through it today. Basically, we're trying to prove if the transformation from Rn to Rm is a matrix transformation, then T of 0 equals 0. That is, T maps the 0 vector in Rn into the 0 vector in Rm. So if T, or the transformation from Rn to Rm, is a matrix transformation, then we can represent the transformation as a matrix multiplication A times x1, the vector x1, x2, xn equals y1, y2, ym. If the vector in Rn is a 0 vector and the product A, and that 0 vector is defined, then the resulting vector will be a 0 matrix, because no matter what A is, anything times 0 is 0, and 0 plus 0 is equal to 0. Therefore, T of 0 equals 0. That is, T maps the 0 vector in Rn into 0 vector in Rm. A little bit of implied what's going on with matrix multiplication, but it's good enough for today. This last true or false question for 1.8 was basically saying, are there linear transformations that aren't matrix transformation? And I said false, because I think the book defined them as synonymous. Linear transformation is a matrix transformation, and a matrix transformation is a linear transformation. On that note, that's it for 1.8. We're into 1.9 now. 1.9 is on composition of matrix transformations, very, very similar to composition of functions. So what is a composition of a matrix transformation? It's a matrix transformation performed on an image vector that resulted from another matrix transformation. So it's a matrix transformation of a matrix transformation. T transformation B of transformation A of vector X can be written as basically T transformation B TB circle TO, or TB circle TA, and then we're kind of getting into this theorem and proof about why matrix multiplication is defined in that unusual way. And it has to do with composition of transformations and making sure that a composition of matrix transformations equals something. Somehow it keeps it symmetric and equal. So I'll learn more about why matrix transformations or matrix multiplication is defined the way it is and how it relates to matrix transformations tomorrow. So that's it for today. Talk to you tomorrow. See you.